Okay, we are solving linear differential equations. The only difference is that we're now going to use a boundary condition to find the plus c. So hopefully by now we're getting into the process. This guy is good to go, right? It's already in the correct format. So I'm going to find P of t, which in this case is negative 2t, and Q of t, which in this case is this guy. And then find the integrating factor. And the integrating factor I of t is found by this fella. So it's going to be e to the integral of negative 2t dt. And this is what basically just negative t squared. And there really isn't any style points on this. Sometimes there is, sometimes there not. This is one of the situations where there's nothing we can do. So we're moving on to solution. Well, the solution normally would be called y, but now it's going to be called v. And it's 1 over the integrating factor. The integral of those two guys plus c. So it's 1 over e to the negative t squared, the integral of e to the negative t squared times this guy. Plus c. And then something really cool happens. Won't those two essentially cancel each other out? Right? E to the negative t squared times e to the positive t squared gets you e to the 0, which is 1. So that means that we now have, it's almost like magic, a very simple integral. So it's, oh well, let's fix that. Is there a better way of rewriting 1 over e to the negative t squared?
E to the t squared.
Yeah. Right, if you integrate this by the power rule, you just get t to the power of 5 plus c. And I think that one, as far as style points go, I think that's as good as it's going to get. Would you agree that's pretty nice? Can't really do much more. Normally that would be the finish, but now we're going to introduce this boundary condition. What you're essentially saying here is that when t is 0, v is 3. And what that's going to allow us to do is to take this general solution that we found and find out who plus c is. And that will then be a particular solution. So I know that v is 3 when t is 0. So e to the 0 is 1, 0 to the 5 is 0, and c is c. So that's 1 times c. So that's basically just c. And now I know c, we got the final answer. It's this fella, t to the 5 plus 3. Are we comfortable with that? Any questions, or can we move on to our next guy? If you're interested, this is a version of question 13. If we are cool with that one, I shall move on to another one. Don't want that one, don't want that one. What's that going to be like? No, I won't do that one, do I? I'll do this one. We have an x squared derivative plus 2xy equals natural log of x, and the boundary condition is that. Is this in the format that a linear differential equation needs to be in, or will I have to fix this?
Yeah, you'll have to get the x's out.
Okay, so if I divide everybody by what, x squared, we get that. Agreed? For a linear differential equation, this has to be 1, right? There has to just be y dashed on its own. So a function of x, or at least something with a y, equals a function of x. Now, that means we can identify the p of x, which is this fella, and the q of x that we're going to use later, which is this fella. So that's typically the second step. And we're getting really good at identifying P and Q, right? Done enough of those, I think. I think we probably should be really good at these. Calculating the integrating factor Ix. Okay, if you integrate 2 over x, you get 2 log x. I need to do some style points on this guy.
X squared, or natural log of x squared.
Agreed. Which then becomes x squared. Are you happy about how this got created? So I should be able to put this together now and get the solution. 1 over the integrating factor, the integral of the integrating factor qx plus a c. So 1 over an x squared, the integral of an x squared times a natural log over an x squared, which is good news. Can you see a little cancelling going on here, which is very common? Happens a lot. We have this guy. Okay. I need to find the integral of log x. Now, if I was going to do it from scratch, and maybe that's the only way you'll be able to do it, if I was going to do it from scratch, I would actually do integration by parts. But I've done the integral of log x at least 3 times now. At least 3 times. Does anybody know what it is? The integral of log x. It's coming. Last chance. Got it at the side here. Whenever you come across an integral that you think could be important or useful, can't you just write it down on this little scratch piece of paper I've got? Do you see that the integral of log x is x log x take away x? So the integral of this guy is x log x take away x. Now, if I didn't know that, or I'd forgotten it, or whatever, here is plan B. You call it 1 times log x. You make this fella the f, and the other guy, the 1, the x. And integration by parts is that guy. So you leave that alone, and you integrate 1. You differentiate that, and you integrate 1. They cancel. And that's where the x log x minus 1, x, I should say, minus x comes from. I'll leave it like that, I think, for the time being. And we've solved the general solution to the differential equation. And now I'm going to use that when x is 1, y is 4. So 4 goes there, 1 over 1 squared. 1 times the log of 1, take away 1, add c. Well, that's 1, so I don't worry about it. The log of 1 is 0, so don't worry about it. So what do I get? I get -1 plus c, which makes c 5. So y is now 1 over x squared, x log x, take away x, plus 5. And we now have what we call the particular solution to this differential equation. Are we happy with this one? Yeah, got nods? We're almost done. We've got a few more. That's it. Let's see who we've got. 16. Yeah, that's interesting. Okay, we got 17. Not that interesting. 18. Let's do 16 next. T cubed dy by dt, 3t squared y is 4 cosine t's, and the boundary condition is that. That t cube's a problem, right? This derivative must be on its own. So I'm going to divide everyone by t cubed. If you divide this guy by t cubed, you get 3 over t. If you divide this guy by t cubed, you don't get anything really except that. I now have it in its linear differential equation form. That's P, and this is Q. Integrating factor is this guy. I'll let you catch up. Pretty straightforward, right? P and Q are what you'd expect. And when you eventually do this guy's integral, you get 3 log t, which is a log of t cubed. And then E and log are inverse functions of each other. So when they work together like this, you essentially, they cancel each other out. And what's left is a simplified answer. And what's left here is t cubed. So far, so good. So we move on to solution. This guy. Okay, we have 1 over t cubed. The integral of t cubed times this guy. Oh, something really nice happened. The t cubes cancels out and we just have to integrate 4 cosines. And 4 cosines when you integrate them, you get 4 signs. And there's our general solution. We don't really need to, I don't think anyway, distribute the 1 over t cubed. I mean, you could call it t to the -3 if you like, but I'm not sure that's any better. Because you get 1 over t cubed, t to the -3, I mean, it's 50-50, I don't see any benefit. I don't see any benefit in distributing it either, although you could. There's a kind of grey area about what's the prettiest form. And so I'm just going to leave it in that form. Now, if you tell me that when t is pi, y is 0, then y goes 0, 1 over pi cubed, 4 times the sine of 0 is going to plus 0. So I have 1 over pi cubed, nothing plus c. Oh, I wasn't expecting that. What's the value of c?
0.
0. I mean, it's okay, you know. C could be 0, right? It could be 42, it could be -1,000,000. So our solution is 1 over t cubed times this guy. So I guess I could just put it in as one big ugly fraction. Have we any questions about that one? Or do you feel comfortable about the process? Good to move on? Okay, we've got about 2 more questions and we are done. I'm not getting too much negative feedback, so I'm assuming that's a good sign. It's 18, like, yeah. I'm going to do part of 18, but not the whole thing. Oops, I misread it. Sorry, I'll do it again. This guy, this differential equation, is not in the format that it needs to be. It needs to look like this guy. And it doesn't. A couple of things wrong with it. You agree that x shouldn't be there. But shouldn't that y not be on the right-hand side? Shouldn't it be over here on the left? Right. So you can do it whatever order you want. I'm just doing it this way because I felt like it. I'm going to subtract y from both sides first. Then I'm going to divide everybody by x. You okay with that? Divide each term by x. That tells me that p of x is -1 over x, and that q of x is this guy. P is this, Q is this. The integrating factor is E integral of that guy, which is -log x. Okay, style points here. I should be able to do something with e to the power of negative log x.
Just a quick question. Are you missing
Yes.
the prime symbol on the first part of the equation, or
I
which is
am.
y minus?
Yeah, it's in. You're right, I missed it. Okay, how'd you make that look good?
Could you turn into e to the natural log of x to the negative 1?
And then you get that, exactly. So you get x to the negative 1. Now, if you don't change that into this, you're going to have a lot of trouble when you do the solution, right? Because it's going to look massively ugly and you won't be able to integrate it. But if you do this, it's going to make the solution a lot cleaner. And our general solution then is going to be that guy. The integral of x to the negative 1 times 7x sine x style points. A better way of saying 1 over x to the negative 1.
X.
If you multiply x to the negative 1 with a normal x, don't they essentially cancel each other and you get 1? So that means that our integral has now turned into a really nice integral. I'm almost at the point where I'm going to stop here. So that's going to be x negative 7 cosine x's, because that's what you get when you integrate a sine, plus c. And that guy is our general solution. I'm not going to do the bit when x is pi, y is 0, but if I did, wouldn't that get me c? And you get what you get. Are we cool with that? I'm just not finishing off the number part. Our last question then. Whoa, would you look at that guy? He doesn't fit quite into anything that we've seen so far, but it is a linear differential equation. But it has some, well, it's quite a few issues. Let's deal with the first issue. It doesn't look like that. You're not allowed y minus 1, right? Can't have y minus 1. Yeah, I've got it. And I've got to figure a way of fixing that. What do you think my next line of working is going to look like? How am I going to fix this so it's closer to looking like this?
Would you divide everything by 3x so that you can get rid of the minus 1?
The short answer is no, but I like your thinking. But no, I'm not going to do it that way. I'm going to get rid of the minus 1, but not the way you suggested it.
Would you distribute?
Yes. Now, would you agree that that guy is a problem, the x squared plus 1? Less obvious, would you also agree that that minus 3 shouldn't be on the left-hand side? So I'm going to take care of the -3 first. And I'm going to do that by simply just adding 3 to both
Wait,
sides.
shouldn't that be a -3x?
Yeah,
Thank you. Yeah. I'm going to get rid of, quite right. I'm going to get rid of that by adding it to both sides. Are we comfortable with that step? Right. One more step and we are done. Stick a fork in it. It is done. What do I need to do now to get it to look like this guy?
Divide by x squared plus 1.
So right off the bat, wasn't that quite an ugly one to just fix, just to get it into the form that we could use linear differential equation technique on, right? Now the P of x is quite messy. The Q of x is by sheer coincidence exactly the same thing. P of x, Q of x. Now the integrating factor comes next. Uh-oh. I don't think we've had many questions where finding the integrating factor was that difficult. Right? Most questions you could do it in your head. We do have a problem this time. Would you agree that you can't do that in your head? Or at least it wouldn't be a good idea. Any suggestions for how I find this integral?
U sub.
A U sub. And if you do a U sub, which is the right thing to do, you differentiate, you get 2x. You do the crossover. And then finally you isolate. The dx. So this guy becomes 3x over u times 1 over 2x du. After some cancelling, you get 3/2 1 over u. That becomes 3/2 log u. Oh, I wish I'd given myself more room here. That's 3/2, the natural log of u is a 3/2. And then replace the u with this guy. So what we have is e to the 3/2, the natural log of x squared plus 1. Are you happy about how we finally got from here to there? So far, so good. Now, style points. 3/2 this guy is the natural log of this guy to the power of 3/2. Agreed? Multiple of a log becomes a log of a power. I can now use the trick that they essentially cancel each other out. And we have not a very pretty answer, but we do have an integrating factor now.
Just a quick question.
Yes.
After you did the u substitution, you had 3/2 natural log of u to the 3/2, and then where did the 3/2 go when you put the x squared plus 1
Oh,
back in?
I used that guy here. So,
Oh, okay.
okay. So I should have probably just stopped there and replaced it here. So time for solution. 1 over the integrating factor. the integral of ix qx plus a c. 1 over x squared plus 1 to the 3 halves. The integral of x squared plus 1 to the 3 halves times this guy. 3x over x squared plus 1 dx add c. Oh God, would you look at that? That's ugly. Not going to do anything with that. It's ugly no matter what I do with it. So I'll just write it down again. You see this x squared plus 1 on the bottom here? Can't it cancel most of this x squared plus 1 into 3 halves? Right? X squared plus 1 on the bottom cancels with some of this. When you take 1 away from this, you're still going to be left with x squared plus 1 to the half, a 3x, and a dx add c. I'm rewriting that as a square root, and I'm putting the 3x at the front. When you look at that guy, do you see something that is a problem? I do need to integrate that, agreed? But again, it's not something I can do in my head. I need to find that integral. What technique shall I use to find that integral?
U sub.
Yes. Are we all comfortable with x squared plus 1? Why I chose that. So you differentiate with respect to x. Load of repeating myself here because it's very similar to some work we did a minute ago. So we have 3x, the square root of u, times 1 over 2x dx. That's going to get me 3 over 2. I'm going to call the square root a half power. I'm going to add 1 to the power and divide by the new power. Oh, at least that happened. And then I'm going to return the u to x squared plus 1. So this integral is that guy. So our solution right now looks like this. 1 over x squared plus 1 to the 3 halves. This integral, which is x squared plus 1 to the 3 halves, plus c. And then I look at style points. And I think to myself, do you know, I think it's going to be worth it to distribute this. Right? By multiplying each of these terms by this ugly fraction. Because if I do, won't this guy and this guy get me 1? And won't this guy and this guy get me a slightly ugly? That guy. So we had to fight our way through that, but we finally got our general solution to our differential equation. That guy. So I'm going to use our boundary condition now to find C. And in our boundary condition, we're told that. So when x is 0, y is 6. So that's 6. 1 plus c over 0 squared plus 1 is 1. 1 to 3 upon 2 is 1. C is 5. So our solution is now 1 plus 5 over that guy. we're done. The last piece of work that's new work. Homework's covered. Linear differential equations are covered. The entire class is covered. We've done everything we need to do. And there wasn't a fireworks or an explosion or a popper or anything. It kind of just petered out, which is kind of what happens. Okay, say hi, everybody. I will see you all tomorrow.